Any questions about anything? So I will be declaring the format of the final exam in a few days. It will have a choice of research papers that you will need to present on, a report, and a pre-recorded presentation. And I might or might not have a separate part of the exam where I set up a Zoom with you and we do a question and answer session one-on-one. So there are some details I'm still trying to work through them. And I will give you enough notice. I will declare it within a week as to how is the final exam going to be. And regarding homeworks, there are going to be 2 more homeworks. So we have done 4 homeworks so far. There's going to be homework 5 and homework 6. The reason I'm doing 2 more homeworks is because I would like to exclude your worst homework from your grade calculation. So please try to do as well as you can in the remaining 3 homeworks. I mean, the homework 4, homework 5, and homework 6. And with this, if you do perfectly, then if you have had a bad score in one of the homeworks, that can be totally ignored. Please try to do well in the final. Point being that even if you scored low on the midterm, you still have a chance to do very well in the course. And please make the best of it. So, and this is why I was not able to give too much of an extension for homework 4, because I would like to give you 2 more homeworks. If I just drag this out, then I won't be able to give you homework 5 and homework 6. It will become pointless. So, okay, great. No questions? So by the way, next Tuesday, there is a talk by Andy Ballard at DeepMind, Google DeepMind. He was one of the people who worked on the AlphaFold problem. He's a PhD from UMD in chemical physics. He worked with Chris Jarzynski. And he will be talking about perturbation theory by Zwanzig, and as to how at DeepMind, he's using machine learning to do a good job at what you are studying currently. So please try to attend that seminar. I posted the details on Slack. It's next Tuesday, 1 p.m. So it's on 27th April, 1 p.m. Great. So just to remind you, what are we talking about? Our whole setup has been that if you have an n-body system's potential energy, expressible as the potential energy of a reference n-body system, which in principle could be much simpler, plus a perturbation from the same. If we know this decomposition, then Zwanzig's formula tells us that the partition function for the true n-body system is given by the partition function for the reference n-body system multiplied by exp of minus beta un10. And this is called statistical mechanics perturbation theory. It's quite interesting that unlike quantum mechanics, where perturbation theory is always an approximation, in statistical mechanics, this is exact. There is no approximation here. This is an exact formula, unlike QM perturbation theory. In principle, this is exact. In practice, it becomes complicated because all of it boils down to how you do this decomposition. Is your reference easy enough? If your reference is too easy, then your perturbation might be too large. If you go with a small perturbation, then your reference might be too complicated, right? So there is always a trade-off. So in practice, it might become not exact, but in principle, in theory, it is exact. So we use this to derive a formula for the Helmholtz free energy, which we showed that Helmholtz free energy will be reference Helmholtz free energy plus some W1 minus W2 by 2 kT plus order of beta square. So we derived a power series in beta for this, right? And this allowed us to get more higher order terms. So that's one thing we did. And the other thing we tried to do last time, and we nearly finished our job, so we just have a little bit left, is to derive van der Waals equation of state. And please go through those notes. If you missed that class, it was quite an important class, and I think it's quite interesting material. Please go through the notes, watch the video, please make sure you get it right. And the key idea there was that UN, the true n-body potential, is a sum of pairwise terms, right? So it's a sum of small u's that themselves depend on pairs I comma j, and you have to be careful with how you sum these things. So we do the perturbation on this pair term, and we say that u of r is equal to u Hart sphere of r. So we take our reference potential as a Hart sphere, and the remaining part is the attractive part. So we drew this, looks something like a potential, the Hart sphere potential looks something like this. At a distance, it's UHS versus R, it's infinity until sigma and 0 after sigma. And the perturbed potential, the perturbation is purely attractive. What does that mean? Starting from any distance, r is equal to infinity, it tells you to get closer, get closer, get closer, get closer, get closer. It wants you to keep getting closer and closer and closer. That's our U1 of R. This is R. So this is the split we used. We could have used other splits. You're welcome to go and try. How else can you do? Again, you could have made the Hart sphere more complicated and you would get different equations of state. This is one split that we used. So with this, and I'm not going to go through the whole of math, I want to emphasize one formula, one key formula that is subtle to understand. And I think at least Nathan got the gist of it last time, and I'll make sure everyone is really clear on what we do here. We said that the value of the full n-body perturbed potential energy calculated as an average in the unperturbed system. So what is this? Let me write it down, it's a mouthful. So average of perturbed n-body energy, n-body potential energy in unperturbed ensemble. So what does this really mean? Here, it sounds complicated, but what we are really saying is to take some quantity Q and calculate its average using, so Q is some quantity, let's say that depends on the position of everything in the system. And in order to calculate this quantity Q, we need to draw samples from a probability distribution P of X. And this is the average of Q, right? This is how we define the average of Q when drawing averages from a probability distribution P. So here Q is UN of 1, it is the value of the perturbed potential energy. And the probability from which you're drawing samples is the reference potential energy 0. So this formula, we wrote down using the formula we derived for classical fluids, which was 4 pi r square dr. But here the probability, which is expressed in terms of the distribution function, came from the Hart sphere GHS of R, and the thing that we are averaging stayed as U1 of R. So this is reference, this is perturbation. This is not perturbed. There is a difference between perturbed and perturbation. This is what you get after perturbing. This is the perturbed potential energy, U of R. This U1 of R is the perturbation. So this formula was something we used and it's subtle. So please make sure that you get the gist of it. This is an important formula. This is key in doing the derivation. With that, we were able to show that P by KT for this n-body system will be given by partial ln Zn naught, the partition function for the reference system, by partial volume at constant number and temperature. And we derived the other term, which came out to be minus a rho square by KT. This is something, this minus a rho square by KT term you have seen in your PChem, if you have ever taken PChem, and most of you have, or in your thermodynamics. Here we showed what exactly is A. This A is given by minus 2 pi integral from sigma to infinity of the attractive part of the potential, U1 of R, R squared dr. And this was cool because in a moment we will tell exactly what is ln Zn naught and what is this first term, but this is quite cool because if you can measure the pressure as a function of density, you fit your pressure as a function of density to this. How will it look like? As the density increases, the pressure increases or maybe decreases, some curve. You fit it to a curve that looks like T1 rho plus T2 rho square. Once you fit it, this T2 will tell you something about A. And from A, you can learn the information about U1. So you can infer the short range, you can infer the attractive part of the potential by fitting your pressure to density. So that's why it's so cool. But we haven't yet talked about, let's call this equation number 1, and let's call this equation number 2. In equation number 2, we haven't yet talked about what is ln Zn naught and how do we differentiate it. So Zn naught is the partition function for the reference hard sphere system, right? HS system. How do we write it down? And it is for the full n-body system. And we are going to differentiate it with respect to volume. So this will have a product of two things. This will have position partition function multiplied by momentum partition function. And we can write down both of them. But given what we seek in equation 2, should I care about the momentum partition function? Any ideas? Should I calculate it or should I not? I'm waiting. People can speak, right? It's not that I cannot hear. Kishla is nodding his head. Kishla, help me. I cannot hear you very clearly. It's okay. Anyone else wants to help me? Kishla has confirmed that I can indeed hear you all. So who wants to help me here? Jessica. No, Nathan, you helped last time. I want Jessica to help me. Sorry, Nathan. I'll come back to you later. What do you think, Jessica?
If it's just a hard sphere system, if it's in equilibrium, I would expect no motion. So then maybe we might want to remove the momentum.
Why exactly? So momentum will depend on, okay, so your hint is here. Can you take this into account and tell me why it's okay to remove the momentum?
If the volume is fluctuating.
So the key idea here is that the position partition function depends on R, right? And momentum partition function depends on P, the momentum, right? Its name is momentum. In other words, this does not depend on volume. Now, can you tell me why it's okay to ignore?
Yes, since we are considering change in volume.
We're differentiating it, right? So it will be zero. There is no dependence with respect to volume. That part will, and also because of the wonderful things of log, right? So log, if it was not log of Zn naught, then would be in trouble. So this will be log position partition function plus log momentum partition function. So when you differentiate this with respect to volume, this part will go to zero. That's why we can ignore it. Thanks, Jessica. Nathan, I'll come back to you. I know you're eager to answer for another question. Great. So we don't need to worry about it. And this tends to be quite true in general. This is not just true for hard sphere. You will be hard pressed to find systems in equilibrium statistical mechanics where momentum partition function depends on the volume. It's the key idea. And this really boils down to the kinetic energy depending only on speed or momentum and potential energy depending only on position. So for most systems, anytime you see differentiation with respect to volume and you have a partition function, you can ignore the momentum part. You don't have to worry about it. It matters. It does play a role in the partition function, but when you differentiate the log of the partition function, it disappears for this reason. So this is something simple, but quite important. So now, all right, let's go to Nathan. So Nathan, since we have agreed that the momentum partition function can be ignored, let's just talk about the position partition function for n hard spheres. Can you tell me what would it be? Of radius sigma. What would it be?
I guess it would be like related to the amount of volume that they can like move in.
Precisely. So correct. So let's say the system is in a box of volume V. Okay. So each thing, if the hard sphere radius had gone to 0, then this integral would have been V to the power n, right? But now we will have to subtract something from here. Can you tell me what will it be, Nathan? This is your hint.
Was it just the volume of each sphere?
Yes, correctly. Do you remember the formula?
Pi. What?
4 pi sigma cubed by 3.
Yeah, 4/3 pi r cubed.
Yeah.
Or sigma cubed.
Right. But here we have forgotten one thing. We have to also, this is not quite right. Thanks, Nathan. This is not quite right. We have to understand that this is the volume for one sphere. We have to account for the volume of every sphere. So that will be 4 pi sigma cubed by 3 multiplied by n, whole thing to the power n. And then we also need to account for that we have double counted. Every sphere is contributing twice, so we have to divide by half. So truly, the true answer here is 1 minus. And if you don't really like the half, that's okay. But it's an approximation which seems to work quite well. So this whole thing will be V minus NB to the power n, where B is equal to 2 pi sigma cube by 3. Okay, so this is my Zn naught for the n particle n hard spheres. My Zn naught is given to be this. Now we can go and calculate our pressure from this. So what did we have? We had P is equal to partial ln Zn naught. No, don't access my photos, good notes. It's partial ln Z naught by partial V at constant n comma t minus a rho square by kt. So let's calculate this thing over here. So we have Zn naught is equal to V minus Nb to the power n. Therefore, ln Zn naught is equal to n ln V minus Nb, right? So when we differentiate this partial ln,
yeah, Professor, wasn't that P by KT?
Oh yeah, good call. Sorry, P by KT, yes. If I was a true physicist, I would say it's pressure in the reduced temperature unit, but you're right, it's P by KT. So partial ln Z naught by partial V at constant n comma t is going to be simple because this n can just be treated constant. So it will become 1 by V minus P multiplied by partial B by partial V is equal to 1. So n by V minus NB is equal to 1 by V by n minus, or actually let's not do that. So this is equal to n by V minus NB. Let's take this and divide both numerator and denominator by volume. So this becomes 1 minus n by VB. And we know n by V is the density of the system. So this thing becomes rho by 1 minus rho B.
Excuse me?
Uh-huh.
Can you go back to the last page? So here the insertion of B is still due to the considering of the size of the hard sphere, right? Mm-hmm. So there's no difference from the original derivation of the van der Waals equation of state in the thermodynamics, right?
Yeah, the difference comes for this. That's the whole idea. The reference system should be so simple that you can explain it to a hard body system, to a high school student. Sorry, not hard body system. Yeah, the reference part is really, really simple. The whole difference, the novelty comes in calculating this part, that we have been able to give a physical sense for A, correct?
I can't see your cursor. Can you?
I will move color here. Do you see?
Yeah.
That is the new part.
Yeah. So yeah, I can understand. So all
the reference part is trivial.
perturbation theory.
Huh?
So the perturbation theory comes into play and becomes different. Just resides in the A part, right? Like
correct. Because the whole idea in perturbation theory is pick a reference system so easy that calculating Z and naught is very, very easy.
Okay, so in that case, is the perturbation theory cannot give us any more meanings on the B, except for
no, it cannot, because we removed that in the reference system. You're right.
Okay, gotcha. Thanks.
It cannot, which is kind of sad. And I'm sorry for spoiling your day, but it cannot. I wish it could, but it cannot.
Yeah, thanks. That's clear.
I mean, it's disappointing, but what can I say? That's the nature. So this is, so now use 4 in 2. This is the same as equation 2. Yeah, you made a very good point. Perturbation is not going to tell us anything about B. That's completely a property of the reference system. It tells us about A. It's a very good point. If I wrote a textbook, I would mention this in the textbook, but I don't think I'm going to write a textbook. There are too many textbooks on StatMech anyway. So P by KT then becomes rho by 1 minus rho B minus A rho square by KT. This is van der Waals equation of state. And as you commented, the B is nothing but the 2 pi sigma cube by 3. It's half the volume. But due to this perturbation theory, we have been able to get good insight into what is A. A is minus 2 pi sigma to infinity U1R R square dr. So you can see that this is really the attractive part of the attractive force, which is leading to this second term in the van der Waals equation of state. So this is an example of how can Zwanzig's perturbation theory be of use. This is just one example. Zwanzig himself in his paper had 5 papers that year that he showed everything how it could be used in 50s. That was super cool. I think this was his PhD work, just to give you a sense. In 50s, you had to do theory like this in your PhD work. Over the years, Zwanzig's perturbation theory has been used in drug design heavily, like in a very, very big way. I would say it's like $1 billion industry, if I'm not kidding, where perturbation theory is used. In fact, there is a company called Schrodinger, which funds my lab also partially. It's listed on NASDAQ, and their main product, they sell stocks there for like $100 a stock. And one of their main products is free energy perturbation. It's called FEP, and that they use to design drugs. So this idea of using equation number 1 is extremely practical. And just to remind you again that unlike quantum mechanics perturbation theory, equation 1 is exact. For real systems, you end up making approximations because this integral average of an exponential is very hard to calculate. So you always end up making approximations, and that's where it becomes perturbation. So we are at a point to start a new chapter in StatMech now. Before we do that, let me just very briefly summarize what we have done so far. So it's been a while. This is our 11th week or something like that. So we have really done our semester in 4 parts. In the first part, we talked about ergodicity, and which led us to a discussion of different ensembles, right? And our whole idea was to really start from the microcanonical ensemble and then look at more complicated ensembles like canonical ensemble or grand canonical ensembles as little systems embedded in a much bigger bath, right? That was the idea. We took a system and thought about it as being embedded in a big bath, and these were connected to the microcanonical ensemble through Taylor series. So we derived the theory for all of this. We showed how partition function connects to thermodynamics. For example, we showed how entropy is equal to KB, ln, omega, NVE. We showed how the Helmholtz energy is equal to minus KBT, ln Q, NVT. And similarly, we showed about the grand canonical potential, which was, where was this sign? It was ln Z mu VT. Do we have plus or minus here? Plus KBT or minus KBT? I keep forgetting. Anyone remember? It's minus. You all should remember. You are the ones taking the exam, not me. I could have derived in a moment, but yeah, so that's minus KBT, and this was connected to pressure times volume. So we derived our connections between these. We also looked at fluctuations. And in the end, it was always about manipulating, differentiating with respect to some variable, the log of the partition function, as you saw even today in class. That's the story always in this first part. In the second part of the semester, we took this. So what am I doing here? I'm doing a very overall bird's eye view recap of SEM so far. Then we applied this to non-interacting systems. In non-interacting systems, we looked at phonons, we looked at photons, we looked at electrons, we did all kinds of funky things. We looked at heat capacity in great detail. And we saw how Einstein was a bit lazy and Debye was more hardworking. And we saw Boltzmann, Stefan Boltzmann law and all those things. We also looked at Fermi-Dirac and Bose-Einstein distribution. We showed how both of these at high temperature and low density reach the classical ideal gas limit. We had some interesting discussions about the approximation of 1 over n factorial, when it works, when it does not work. We discussed all these things. Then we moved to part 3, where we looked at interacting systems. Interacting systems really means that we have a complicated n-body potential that depends on R1 to Rn, and it's not equal to 0. For this, we developed and we mostly looked at the formalism for classical fluids. We talked about the distribution functions. We had a whole hierarchy of distribution functions, but our key hero here was G of R, which is the radial distribution function that we talked a lot of time talking about. In this part, we then developed a formalism to calculate properties of interacting system by using StatMech perturbation theory. And I showed you how through this, you can get the equation of state for a van der Waals gas by taking Hart spheres as your reference system. And we did things like that. And I told you that it can be actually much more powerful. I did other things also, but I'm just trying to tell you the things that you will probably remember. Hopefully you will remember once the semester is over, what was the big picture. Now we are ready to move to part 4 of the system, which is of the semester, which is quite a lot of fun, which is phase transitions and critical phenomena. Mostly, I will talk about phase transitions in this, a little bit about critical phenomena. And here we are going to spend some time talking about a very popular model in physics called Ising model. Ising model has led to at least one Nobel Prize, which was on Sagar. One could argue that it has led to a second Nobel Prize, which was Wilson in 1970s. And I think there is scope for more Nobel Prizes. I will mention to you some of the open problems in the field. So you can go and solve them. If you do them, you might get the Nobel Prize. It's very, very likely. If not Nobel Prize, you will get some Abel Prize or something. You will get a lot of money. It's quite likely. So many of you might have seen Ising model before, so it will be familiar to you, but I'm going to start in a very, very basic way and introduce to you what's going on here. It's a simple model, but it tends to be extremely powerful for modeling things such as social networks, for modeling polymers, for modeling ions, for modeling neurons in the brain, anything you want can be modeled using Ising model. In fact, when I was an undergrad, I had papers modeling stacking faults in a crystal using Ising model. So it's extremely powerful. You can model anything you want using Ising model. So physicists and chemical physicists especially love it. In biology also, it's used a lot, as I mentioned, for example, firing of neurons. So the idea in Ising model comes from follows. Imagine it really, we talk about magnets for this, even though we really don't do much with magnets in this, but we will talk about magnets and magnetizations. So let's imagine you have these tiny magnets that can take north, south, south, north. So you have these magnets that can point up. When it points up, it means north is up. When it points down, it means north is down, okay? So instead of writing NS, NS, I will write it as magnets that look like up, 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 down, down, up, down, 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 up, dot, dot, dot. I have lots of magnets in 1D, okay? Ising model will be very quickly generalized to higher dimensions, and that's kind of the most important part of this part of the semester, that we will work with any dimension, and I will talk about phase transitions in general, in generic dimensions. Some of you might even be interested in phase transitions in 0 dimensions. Does anyone know what's an example of a system in 0 dimensions?
A quantum dot.
Quantum dot. So we won't be talking about quantum dots. We will start with 1D. What's an example of a system in 1D?
Quantum wire.
Quantum wire or carbon nanotube could be considered as a 1D, right? If it's fine enough. What's an example of a system in 2D?
Graphene, I guess.
Graphene, I guess, right. So one of the key things we will be showing here is that a 1D system cannot have phase transitions. In order to have phase transitions, you need to go to at least 2 dimensions. And we will be going into details of this intuitively and mathematically, and we will be developing formalisms to study this. So we will first look at the whole picture through some intuitive processes. Then we will go to something called mean field theory. And after that, we will spend a little bit of time talking about something called renormalization group theory. And that will probably be the last topic of the semester. And that will be done. So let's think about these magnets that can point up and down. And now let's say these are my tiny magnets that I've kept on my table, and they are just along a line. Now I bring a massive magnet, a huge, huge magnet that says south, north. Okay, I apply an external magnetic field. What will be the effect of this external, in the presence of this external magnetic field? How will these little tiny magnets look like? And for now, let's assume that they don't talk to each other, okay? Let's say they are just kept next to each other. They are stacked around, but they don't really talk to each other. So how will they look like in the presence of this magnet? Any idea?
They will orient themselves according to the field.
So how will all of them point up? Will all of them point down or something else?
All of them point down.
All of them will point down, right? They will get aligned due to the effect of this external magnet. If your external magnet was oriented like this, then all of them would point up. So the ground state of the system depends on the...
Yeah, small question. So when you say magnet, are you referring to like a uniform magnetic field through that region? Or...
Yeah. This is everywhere.
Okay. Cool.
This is everywhere. It's effective.
Oh, yeah. Okay, fine.
Okay. So now let's try to make this mathematical. Let's say that every magnet has a magnetic moment mu. So this one corresponds to plus mu, plus mu, plus mu, plus mu. In this case, it would be minus mu, minus mu, minus mu. And let's write down the energy of the system. And let's call this external magnetic field as H. In the top one, H is pointing up. In the bottom one, H is pointing down. So we can write down the Hamiltonian or the energy for such a system in the following way. Again, for now, I'm going to ignore interspin, and instead of the term magnet, I'm going to use the term spin. interspin interaction. Magnet was just to give you some physical intuition, but I'm going to talk of them generally as spin. And I will call this as spin number 1, spin number 2, spin number 3, spin number 4, ... And I have infinitely many of them, let's say. Or let's say I have only I is equal to 1 to n. Okay, so in that case, I can describe this system as minus h mu s1 minus h mu s2 minus h mu s3 minus ... Why is this a good example of a system? Let's good way to write down the Hamiltonian for the system. I'm not saying this is the only way you could have written down the Hamiltonian. I'm going to tell you that this Hamiltonian conforms to the physical picture that I just set for you. So if H is positive, so let's say this one, if H is positive.
Professor, what is S1, H2, S3?
I wrote here, this is the name of every spin. This is the value every spin can take.
Yeah, only the name, right?
Yeah, so S1 can be plus or S1 can be minus. So good, good question. S1 can be plus or minus, okay?
Okay.
So in this case, S1 is equal to plus 1, S2 is equal to plus 1, S4 is equal to minus 1, okay? And in this case, S1 is equal to S2 is equal to S3, everything is equal to minus 1, okay? And in this case, everything is plus 1. So it's the spin which takes the value plus 1 if it's pointing top, the magnetic moment, and it takes the value minus 1 if it's pointing bottom. So if you look at this one, this first, just let's look at the first spin. And mu is positive. The magnetic moment itself is positive. Mu is always kept positive. Now if H is positive, let's say H is equal to 5. So we have minus 5 mu S1. And let's say mu is equal to 1. So we have minus 5 S1. So if in this case, we know that systems want to minimize their energy, right? That's the nature of everything. You don't want to be jumping up and down, except when you have had a lot of coffee. You would rather lie down on the ground, right? You would rather chill on your bed, like Pakoraev, right now chilling on the bed in front of me. So when would this happen? Would this happen when S1 is positive or S1 is negative?
Positive?
Positive.
Yeah.
So force says S1 to be positive. So so strictly speaking, if I go back to my picture, I have a bit of a contradiction because what I wrote here is that when H is positive, I want S1 to be positive. Is that what I'm getting here? No. So instead, physically it's the opposite effect, but we can work in abstract land. So let's look at this system. Let's look at this Hamiltonian once again. Hamiltonian H is equal to minus I is equal to 1 to n, strength of the external magnetic field, moment of every magnet multiplied by the spin. And the way we have defined it right now, it's kind of counterintuitive to what you expect actual magnets to do. So what this is going to do is, so mu is always kept 0. If H is positive, then ground state or low energy configuration is S1 is equal to S2 is equal to S3 is equal to plus 1. So this magnet is such that if you have a big magnetic field, which is positive, pointing in a top direction, all the little magnets will align in the direction of that magnetic field. Okay? This is opposite to what happens with real physical magnets, but I don't think this should make you too upset. This is just how we are describing the system. It takes something and aligns in that direction. The idea is that it orients. If H is negative, then you can see again that ground state is S1 is equal to S2 is equal to S3 is equal to minus 1. and all the spins will align against the, again in the direction of the magnetic field, but in the opposite direction. So this is the Hamiltonian for a system which describes what's going on. However, in reality, the spins talk to each other, right? So we have to introduce a second term. Let's introduce, because this system is not very interesting. Fun really happens when we introduce a second term. Let's introduce a second term accounting for interactions between spins. In order to do that, we take our Hamiltonian, we still write it down as I is equal to 1 to n, external magnetic field H, mu SI, and then we add a second term minus J, which takes the product of two spins for I not equal to J. Okay. Now let's look at this Hamiltonian, and in an opposite case, let's set H is equal to 0. Okay, so there is no external magnetic field, and let's set J positive. Okay, if H is equal to 0 and J is positive, in fact, let's say J is equal to 1, for example. Okay, then what would H be? It would be minus I not equal to J, SI, Sj. In this case, what would be the ground state of the spins? Would they like to, what would they look like? Would they look like this? Would they look like this? Would they look like, or would they look completely random? Any ideas? Who is very confident in what it will look like? Who wants to go?
So the target is to minimize energy, right?
Minimize H, yes.
Yeah, so either the SI, want to be both positive or both negative. That way the multiplication will give us a positive.
Correct.
And
yeah, absolutely correct. So it becomes degenerate, right? All the spins point up, all the spins point down, which kind of makes sense, right? If you have really played with lots of little magnets and you're ignoring that there is no magnet, you must have seen this, right? The magnets can align top, but they can keep rotating. This is a 1D system which we are just aligned top and bottom, up, pointing up and pointing down. But if you are allowed all sorts of rotation, basically it's saying that everything will be aligned, but you can rotate it whichever way you want. So it's doubly degenerate in this case. Now let's go again to remind you, let's look at H is equal to 0 and J negative, let's say equal to -1. So in this case, okay, by the way, this H symbol can become a bit confusing. I mean, I'm surprised no one has pointed out already. Every time this happens, let's call the Hamiltonian actually as E, and let's call it mu as the energy of the microstate. And because every configuration of spins is a given value of the microstate, it specifies the microstate of the system, all spin configurations, okay? And I'm sorry for that confusion. So it's Hamiltonian, but we call it E nu. And this is confusing because the external magnetic field is called H and Hamiltonian is also called H. We will always use E nu for the Hamiltonian. We will reserve H for the external magnetic field. The good news is most of the time we will work with 0 external magnetic field. So it won't matter. This is the only time where we are going to look at external magnetic field. If H is equal to 0, that is external magnetic field, and the interaction is negative, then in this case, the energy of a microstate would be given by, again, I'm setting J is equal to -1 without loss of generality. It will be plus I naught equal to J, SI, Sj. So in this case, the ground state of the system will look like this. All these spins will suddenly be aligned against each other. With one, I have made one approximation here. I'm assuming that strictly speaking, what I wrote down is true if the spins talk to each other only at nearest neighbor distance. If you introduce that spins talk to each other even from here to here, even then the ground state is true, what I just wrote down, but funny things can start to happen when you allow for spins to talk even across long distances. And we'll get into that in a bit. But right now, let's not worry about it. But you can see directly, just by seeing what can be the minimum energy, it will be antiferromagnetic coupling. Antiferromagnetic ground state. So hopefully they gave you a bit of intuition into this, what this Ising model is. So what this Ising model is called is a system. What this Ising model is a system where the energy of any given microstate as a function of spin values, S1, S2, S3, and Sn, each of them can be plus minus 1, and specifying them as plus minus 1 is a full specification of the microstate. There is no momentum here. We are completely out of momentum land. This is what is called a discrete system, okay? There are discrete values that the spins can take, no momentum at all. There is no concept of time. There is no concept of speed over here. It's just a discrete system. This Hamiltonian, or the energy of a microstate, is given by minus I is equal to 1 to n h, which is the coupling with the external magnetic field for every spin, mu si, minus j, I not equal to j, si fj. If you allow, normally what we do here is to consider modulus of I minus j equal to 1, which means nearest neighbor interactions. If you go beyond nearest neighbor interactions, the math can become a bit tricky. So this is a very popular model in StatMech. The Ising model is possibly the #1 most popular model in statistical mechanics for the last 100 years. It will stay and stay and stay. It's not going to go anywhere. Why have there been 2 Nobel Prizes about this model? So the story comes down to this. Let's set external h is equal to 0, okay? And consider E nu is equal to minus j summation I not equal to j si multiplied by fj. For this system, and let's consider j more than 0, okay? So I can talk about the average value of the magnetization. That's why we introduced the notion of a magnet, but really this is much more generic than a magnet. This is just spin pointing up or down. You could have a bunch of molecules, and you could think of the molecules as being in a certain conformation A or a certain conformation B. Boat is A, chair is B, and you could give +1 to the boat and -1 to the chair, things like that. So you could make it very, very general. So let's think about the average magnetization, which will be given by going to every spin, I is equal to 1 to n, looking at mu and calculating the average value of that spin, right? So in the presence of, so we are thinking about h is equal to 0, j and the j more than, and j positive. So in this case, if I try to think about how will the average magnetization look as a function of temperature, physical temperature of the system, what do I expect to happen at very, very high temperatures? This, what Kishler pointed out, the ground state of the system, everything pointing up or everything pointing down. And to make things simple, I will talk about the modulus of the whole thing, because it could be +1 or -1, right? So at 0 temperature, Kishler just explained, and I hope all of you agree, that the system can be all positive or all negative, right? So that will mean that the average magnetization of the system will be something positive up here. What will happen to the magnetization of the system at very high temperatures? What do you expect? Will it still be here, or will something else happen?
It should be like completely random.
Completely random, right? Because of entropy. You have an energy cost, but we have not talked about the entropy of the system. We will talk about that in a moment. but you expect that disorder will come and prevail, and the systems will be like, I don't care what's my energy of talking to you. I'm just going to do whatever I want, right? So it will become random. It will go to 0. Now, before I go further, I just want to say that this I described for spins in 1D, right? You could also generalize an Ising model to 2D, where your spins could be like this. Up and down on a 2D lattice. This is what we call a 2D square lattice. You could imagine a more complicated lattice where instead of a square, you have hexagons. Hexagon, I'm drawing the hexagon just for visual aid. And you have spins at every corner of the hexagon, every vertex. And they could all take plus or minus value, right? You could even go to 3D. You could start drawing spins by placing them at the corners of the cube, up, down, down, down. And the same Hamiltonian would apply to them also. It's just that you have to number them carefully, right? So here in the 2D example, this will be S1, S2, S3, S4, S5, S6, S7, S8, or maybe you number them some other way, the number so that nearest neighbors have similar type of number. You have to be careful with the numbering. So, and I'm going to stop in 2 moments, but I will give you the key result that we are going to spend the next few classes worrying about is what happens to this average magnetization versus temperature as we increase the dimensionality of the system. So the key result that Onsager was able to show for this model system, which is known for physical system, is that, of course, you expect the magnetization to go down, and then at some temperature, it becomes 0. So this happens in 2D, 3D, or higher. And the temperature at which the magnetization becomes 0 is called the critical temperature. T is equal to Tc is called the critical temperature. This is a temperature so again, imagine your toy magnets, right? Your toy magnets are all stacked along each other. But now imagine that you're shaking the whole thing, right? Temperature is like fluctuation system. When you're shaking the whole thing, if you jiggle it just very gently, the magnets will still stay aligned, right? If you jiggle it like a crazy person, then they will lose all alignment, right? So at some temperature that will happen. The key result that we are going to show next time is that for 1D system, the critical temperature is 0. For 2D system, the critical temperature is non-zero. In fact, the critical temperature increases with dimensionality. For 1D, it is 0. For 2D, it is higher. For 3D, it becomes higher, and it keeps going further and further and further. I will give you an intuitive picture next time, which is called, and I'm probably gonna mess up the spelling, Pearl's droplet argument by calculating the entropy of disturbing just one spin and show you why in 1D, indeed, the critical temperature is 0. And in 2D, I will show you why it is non-zero. And these things are quite nice. They have lots of, we can keep talking about this a lot. So I will show you the first droplet argument that Tc is equal to 0 in 1D and not in 0 in 2D. Then I will go to mean field theory, where I will show you that mean field theory, which kind of ignores the individual character of every spin and treats them in an average basis, actually does a terrible job. It gives you non-zero critical temperature in 1D. However, it becomes very exact as the dimensionality increases. As dimensionality increases, mean field theory becomes more and more and more exact. And finally, we will talk about the renormalization group theory, which can give you correct critical temperature even in 1D. In fact, one of the reasons I do science is because one of the first projects I think I did as a sophomore was to calculate the critical temperature for a 1D Ising model. No, for a 2D Ising model. For a 1D, it's 0, right? So you can write a computer code where you do Monte Carlo simulations and allow spins to flip up and down. And Onsager proved for the first time, and if I get the expression right, that the critical temperature in units of kBt is 2 by ln 1 plus root 2 for 2D square lattice. And I might have one of these numbers wrong, but it's something like this. This was Onsager's PhD work. This is exactly true. This result can be verified by doing computer simulations, by doing other theories. And Onsager derived his result in his PhD work. He was later given the Nobel Prize for this. For 3D system, so this is exact result. Onsager's result is exact. For 3D system, there is no way to get exact critical temperature. Exact TC is not possible yet. There is no theoretical way to do it. And this, if you do it, you will definitely get the Nobel Prize. I'm ready to bet $100,000 to you. If some point in your future careers, you go and derive an exact analytical theory for critical temperature in 3D, and you don't get the Nobel Prize, you should come and talk to me. And if I have $100,000 to spare, I will give it to you. In today's value, not inflation adjusted. So it might take enough time that 100,000 might become useless. That's my key here. I'm betting that it will not be for a long time. So people have numerical ways of doing it. Renormation group theory is also inexact. It's an approximation. It's beautiful because renormation group theory says, and we will talk about this in a moment. These all have their own governing physics. But next time we will talk about Pearl's droplet argument. We will restart with this Hamiltonian that I wrote down, and I will show you again in the presence of H is equal to 0. So all of this is in the presence of H is equal to 0, right? Because if you had an external magnetic field, then of course you can have net magnetization even at higher temperatures, right? Is this part clear? Because even in 1D, H not equal to 0 will give magnetization not equal to 0 at T more than 0, right? Because the external magnetic field will just tell the magnets to align. So the key picture here is you have a box with little magnets. External magnetic field is like a big magnet that you bring along with to align everything, while temperature is you shaking the box. So the point being that in 1D, any amount of shaking of the box will cause the magnets to become completely disoriented. It's like Jenga, right? Think about Jenga. When you make Jenga in 1D, if you have played Jenga, you pull anything and everything breaks down. If you have a Jenga in 2D, you can imagine that maybe I do something and it's still stable, right? So higher dimensionals allow system to be stable to these perturbations. But if you have an external magnetic field, that will be like some big person holding the whole block of Jenga together. It's not going to just tumble. So think about all this, read Chandler's chapter. Chandler talks about this, please try to read it. Next time we will again resume here. As we work through Pearl's droplet argument, you will see what it looks like. On the class website, I have posted a link to a web app where you can play with Ising model in 2D. You have to set how many plus spins and minus spins you have in the beginning. You can set the critical temperature. I invite you to go and play with it. As you increase the critical temperature, you will see even in 2D, beyond a height, you can put in this value that I wrote over here. You can compute it and check the value before you put it there from Wikipedia. This result is exact. You can see that as you put higher values of the temperature, the system will just tumble and the spins won't stay. So actually, let me show you that app.
I had a quick question. So when you're talking about like higher dimensions for the magnetization, do you have examples of such systems? Because I mean, I'm wondering that I'm guessing that it's not some crazy metaphysics stuff here, but like in this sort of situation, you should have some sort of realistic situations of higher
sure.
dimensions. And
does anyone want to answer Smithan's question? What's an example of a system in higher dimensions? My guess, my hint to you is you probably played with this network during the course of the class. If not, then this morning.
Oh.
Social network, Facebook. That's a higher dimension system, right?
Ah.
So these things sound abstract. If you're restricting to just reality, it sounds like it's just that. But even you don't even have to go to social network. You can think of a system where dimensions correspond to different chemical species, right? It's just an abstract concept.
Exactly. Yeah.
In order to prove this result about 3D, one of the most important people who has worked in the field is our own Michael Fisher, who is now emeritus, and he was a professor in chemistry and biochemistry. You should go and read it. He nearly won the Nobel Prize. Michael Fisher has papers where he derives the critical temperature 3 minus epsilon dimension. And it is true for any epsilon positive and things like that. You would be like, what does it mean, 3 minus epsilon dimension? That's purely mathematical. But these higher dimensions, you can think of a system with different species compositions being higher dimension. So we can generate many examples. So this app that is on the web page, you can go and play here. You can set up. I aligned everything, and my local magnetic field is 0. And this temperature 2.27, I think, is the critical temperature as per Onsager. Let's put a very high temperature. Let's put 5, and let's see what happens. Where is the start button? Start. It stays random, right? The spins never arrange with here. The blue is plus, the yellow is -1. It stays that way. Now let's pause this. Let's randomize. Let's go to a lower temperature. Let's go to 2. Look, something funny happened. Order is starting to emerge, right? You can also see why this is important for something like politics. The yellow could be a Republican voter, the blue could be a Democrat voter, right? And you're trying to see, can I go and influence my neighbor's view? If the temperature is small enough, you can, and everyone can get aligned in the same way. But if you have neighbors only along 1 dimension, you will never be able to influence them. If you have neighbor in 2 dimensions, you can do that. And that's why social network is also so powerful. Social network is like having neighbors in infinitely dimension, right? You post one thing and it goes and gets announced to everyone. And this is a fun app to play with, and you can do lots of things. If you go to a very low temperature, the same behavior will happen. At very low temperature, it might, the kinetics can start to play a role, and the alignment will actually take more time for it to happen. But yeah, I invite you to go and play with this. It's a lot of fun. Okay, and next time we will derive, we will show how in 1D the critical temperature is indeed 0. And then using this Pearl's droplet argument, I will get you quite close to Onsager's result. I won't get you the full answer. And then we will keep working on all of this. Any questions?
So how come the critical temperature doesn't depend on how many spins you have? Or is it only for a large number of spins?
It's for thermodynamic limit. Very good point. It's thermodynamic limit. N tends to infinity. Nathan, I will point it in the notes. Yeah, all of our stack, we are not doing small system stack, right?
Yeah.
We are always interested in N tends to infinity, volume tends to infinity, N by V tends to 0. Okay. So if you are in your qualifying exams and you get confused about some answer, you can just mumble, thermodynamic limit. It will probably make sense about something. So that's the answer. Good question. Any other questions?
I think even for finite size system, there are still some scalings. Yeah, but
yeah, we will talk a bit about the scaling. Yeah, there are lots and lots of wonderful things that you can do in this. But finite size systems, we will not deal with very much. We will deal with N tends to infinity. Okay, good. Any other questions or comments? So this part is fun. Try to pay attention. It's very useful, and hopefully you will enjoy it. It's a bit different from what we have been doing, but it's a lot of fun. And yeah, and as I mentioned, once again, there will be 2 more homeworks. Please try to do very well in homework 4, 5, and 6, because I'm going to exclude your worst homework from the grade calculation. Okay? And I will give details of the final within a week from now. Okay, see you all later.